Hey everybody, and welcome back to our 6-week webinar, The Magic of Pretest, Post-Test, and Longitudinal Data Analysis. William Bannon of Stats Whisper again, bringing you the presentation. Now our webinar agenda, where are we? So we are at week 2, and as it states on the slide, this is the week where we examine pre-test, post-test data analysis. In other words, if you have pre-test, pre-post data, how do you analyze that statistically? And again, we're going to examine pre-test, post-test data in the context of steps 3 through 6 of the 7 steps of data analysis. So we will examine for pre-test, post-test how to do checks of data integrity, univariate analysis, bivariate analysis, and multivariate analysis. So we have a full plate today. So it will be a rather rapid presentation, not too rapid, just right? So we'll take a cursory view of steps 3 through 5, and we really want to focus on step 6, which is multivariate testing. And if you recall, in pretest, post-test, we have the option of using multiple linear regression or repeated measures, general linear models. So we want to consider both of those. First, we will look at step 3 of the 7 steps of data analysis, which is checks of data integrity. And when we look at checks of data integrity, what we're asking is, are the data appropriate for our statistical analysis plan? Right, so let's delve into that a little. So what value is a study if the findings are incorrect, right? So a study with incorrect findings is not a contribution to the field. It's actually more dangerous, right? So what we have to keep in mind is these checks of data integrity, even a small one missed, could lead to inaccurate findings. So we want to take checks of data integrity very seriously, right? Now, the aspects of checks of data integrity vary by study. For example, different statistical tests have different types of checks of data integrity, right? So it's more the details that they differ, right? So the overall approach, you'll see the 4 areas are the same, but some of the details differ. So our checks are going to be based upon our pre-post design, and they will be appropriate for multiple linear regression and repeated measures GLM. So in essence, if we're using multiple linear regression, we want to do these checks, but if we're going to do repeated measures GLM, we also want to do the same checks that we're doing for the preparation of the multiple linear regression. So it's useful in both contexts. So here we have the 4 areas where data integrity must be checked, right? So we handled the first check last week, right? So we looked at statistical power at the end of the first presentation last week, right? So done in week 1, exclamation point. Check 2, test assumptions, we're looking at in week 2, right? Check 3, missing data, that will be in week 4. And check 4, measurement tools, is looked at in this presentation as well. Now, let's recall specifically what our pre-test, post-test analysis is examining. Right, so recall the study map also from the first week's presentation. Right, so research question 1A, our pre-post analysis. right? So is the happiness intervention associated with significantly higher happiness scores from pre to post test, right? And our hypothesis is that it will be, right? Our experimental group will have significantly higher happiness change than the control. And then we have the dependent variable. Recall again, it's not the pre or the post measure, it's the change from pre to post. That's our dependent variable. Our independent variable study group, and we have covariates, education and income. And then I recall again, right, the image, right? So just a more truncated version of what we just read, right? So we have our dependent variable on the right. We have our two variables that are covariate variables on the left, along with the independent variable. Right now, how are we going to express, right, that dependent variable? So it's not the pre and it's not the post, it's the change. We can express the change in different scores. Specifically, we could minus the pre-test from the post-test. It'll create one score that reflects the degree of change. Right? Those different scores will be the dependent variable. So here's how to compute the change scores in SPSS. Now, if we actually want to implement that in SPSS, here's how we do it. So we go to transform, right? We go to compute variable, right? So we give the target variable, that's our difference scores, a name. For example, we might call it difference pre-post. Right? No spaces, please. Difference pre-post. And what we do is we put the post test in and we minus the pre-test. Now remember, haste or paste. So OK or paste, we can click OK and it'll run. But what if we put the wrong names up there? So we want a paper trail, so we click paste. That's just because the variable's in there already, right? So then to run it, we highlight the syntax and we click the big green button. Right, so since it's there already, let's take a look. So there it is, difference pre to post. And then you could even see right here, this person got a 2 at pretest and a 2.8 at post-test, and the difference is a positive 0.80, right? So that's the difference, right? It's an increase of 0.80. And that's our difference scores. Now, something that's important to keep in mind is happiness, right? Those happiness scores at pretest and post-test are both measured on a scale of 1 to 5, with 5 being more happy. So when we minus them to create difference scores, the most positive change would be if they had a 1 at pretest and a 5 at post-test. So the highest positive score would be 4.0, and then vice versa. The most negative change would be a negative 4.0, 5 at pre, 1 at post. And a score of 0 means no change from pre to post. So the different scores express exactly what we're looking at, the change from pre to post. So keeping in mind that we're looking at our different scores here, let's look at our test assumptions. So first we'll look at check 2, test assumptions. So when we're doing multiple linear regression, or almost any parametric F-test, which is also the repeated measures GLM, we want to look at equivalence of variances in several ways. First, the normal distribution. B, influence of outlier scores. Then linearity, homoscedasticity, multicollinearity. Those are the major ones we'll consider here. There's a few others, we won't address them here, right, such as homogeneity of variances. But typically, if these bigger ones are okay, the smaller ones will be handled. So the first thing we're looking at is a normal distribution of scores, right? So normality. So if we have a continuous variable, we want the scores to be normally distributed, right? So what does that mean? Well, you got this bell shape right here. That's the classic bell shape in research. That's the distribution of scores. The center is the highest because that's the average score, right? So you'll see in the center bottom, the 0, that's the mean score. It's the average score where most people are. And the other people are clustered right around there. For example, in a normal distribution, you'll see that 68% at the top with the 2 lines. What that's indicating is between that -1 and +1, there's 68% of the cases. Now the -1 and +1 are standard deviations, which means it's a measurement of dispersion of the cases. So basically what it's saying is 68% of the scores are going to be clustered around the mean within that one standard deviation, above and below the mean. So if our difference scores, right, our happiness pre and post difference scores were normally distributed, we know the mean is 0.18, we'll see that in a minute, and the standard deviation is 0.25. So if we minus 0.25 from 0.18, right, to the left, that's one standard deviation below the mean, which is negative 0.07. If we add one standard deviation to the mean, 0.25 plus 0.18, that's a positive 0.43. So that's one standard deviation above the mean. So if our difference scores were normally distributed, we would see 68% of the cases, right, the scores, 68%, roughly 2/3, would be in between negative 0.07 and positive 0.43. However, if we look at the actual distribution of our difference scores, right, so that was theoretical before. This is the actual distribution of the scores. There's only 45% of the scores in between that one standard deviation interval. In other words, the scores that should be in that interval in a normal distribution are actually outside the interval. They're higher and lower than negative 0.07 and 0.43. So we only have 45% of scores. So our question becomes this: even though the percentage is not perfectly normal, does this distribution still approximate a normal distribution to the point that it would meet the assumption of normality? So one way to tell this is to look at the skewness, which is the peak, right? The skew refers to if the peak is in the center of that distribution in the bell shape, right? If the peak, the skewness is 3 times the standard error of the skew, right? And we're going to look at that in the output. So it will become very clear very soon. And then we also want to look at, regarding the kurtosis, that addresses the spread of the cases to the tails, so not in the peak, but out to the sides, is the kurtosis 3 times the standard error, right? So there's many methods. This one, so there's a lot of ways of figuring out normality. Many of them are sensitive to sample size. So this is a good solid way of looking at normality, even if you have a small sample of about 100 like we have. So this is how to compute that in SPSS. This is the same procedure as running the descriptives, the univariate analysis. So we'll be doing that later, so we won't do it here, but this is the way to produce the skewness and kurtosis. And the values you get are as so, right? So we see the skew is 0.68, and the standard error of the skewness is 0.24. So if we divide the skew by the standard error, we have a ratio of 2.83. So it's below 3. So we could say the skew is approximately normal. And then the same with the kurtosis. The kurtosis is negative 0.64. The negative doesn't matter. And the standard error of the kurtosis is 0.48. So if we divide the kurtosis by the standard error, we have a ratio of 1.33, which is far below 3. So we could say that the distribution is approximately normal. So we do this with our difference scores because it's a continuous score. So we would also do the same procedure with other continuous variables such as our income variable, right? And any continuous score you have within your study. Now, outliers. Outliers are extreme scores, right, relative to the average score. They can be extremely high or they can be extremely low. So they're rather insidious, meaning that they can cause a whole lot of trouble in your study without you seeing it. So sometimes just one outlier score can actually drive findings. So something statistically significant, but that's only based on one or two outlier scores. And that's not a true finding, that's more of an aberration. So we want to make sure in our study that we're not being fooled by the outlier scores. So the first step is to identify if there are any outlier scores in the distribution. Now recall the distribution had the little standard deviations at the bottom. If a score, we could define an outlier as a score at least 3 standard deviations from the mean, and we'll illustrate that in a moment. Then we want to see if the outlier has that undue influence on our study results. Remember, because it's not the outlier that's problematic, it's the undue influence it has on the study results. Right? And in our case, because we're looking at different scores, an outlier would be someone that had a huge change from pre to post. Right? So if somebody had a full maximum 4 change from pre to post, that could be one outlier score that could make the whole intervention look significant, but it was only that one person's change that causes that. So then we want to look at, do the outliers change the findings in terms of, say, statistical significance? So again, the way we would find out the standard deviations relative to the mean would be to compute, and we're going to do this again in univariate analysis, but run descriptives and just compute the mean and standard deviation in SPSS. So you'll see when we get to that part that the mean again is 0.18 and the standard deviation is 0.25. Now shortly ago we computed one standard deviation from the mean, so this is the same thing, except it's 3 standard deviations from the mean. So 3 standard deviations, so the standard deviation is 0.25, so 3 of them are 0.75. So if we minus 0.75 from the mean of 0.18, we get negative 0.57. Right? So scores below negative 0.57, below the mean, are low outliers, extremely low scores. And then the other way, we would add 3 standard deviations to the mean, so 0.18 plus 0.75 is 0.93. So we would define outliers as scores that are either less than negative 0.57 or greater than 0.93, right? So in practical terms, we would say 0.93 is a big change from pretest to post-test regarding happiness difference scores. So anybody that gets around a 1-point change from pre to post is going to be a real outlier score. the way we would check that is go to the frequency table produced in SPSS when we ran those frequencies, and it lists the actual scores. So we look at the list of scores, and we see the lowest score is negative 0.20. So it's nobody got even close to getting a change from pre to post of negative 0.57. The lowest was negative 0.20, so no outlier there. And then the high outliers, right, 0.93 and above, the highest change from pre to post was 0.80. So there are no actual outliers in this distribution. So we might say that's all well and good in the context of this study, but typically there are at least one or two outlier scores. So what if there are outlier scores? What's our next step? Well, we want to create a version of the variable with and without the outlier score, right? So let's look at that really fast in SPSS. So for example, if we did have an outlier in the pre to post, right, there's plenty of ways to look at this and to score it. One of them is if you right click here, you can insert a variable, then you can actually cut and paste, right, our difference score. So we might call this difference no outlier, right? Diff no outlier, right? And then we go back to the data view. Right, so difference, no outlier. Now let's say that 0.80 was an outlier, right? Or the highest score was. We could simply right click, sort descending, right? Then the highest scores come to the top. Then, there's plenty of ways that one of them is to actually just delete the outlier score and then be very paranoid and actually go down and look from case to case to make sure the variables match exactly. And I'd probably go all the way to the top to the bottom. Like I said, just out of a sense of fear of anything going wrong. But then you have a version of the variable with the outlier and without the outlier. Okay, so that's what we want. Right? Then we would conduct the same statistical test, like if we were doing regression or something of that fashion, using the variable with the outlier. Then we would repeat the same test with the variable without the outlier. Then we would see if the findings are similar. For example, do you get statistically significant findings in both tests, right? Or is one significant and the other isn't, right? So if one's significant and the other isn't, that may indicate that undue influence of the outlier. The outlier is either causing significance or causing not significance, right? So you should consider excluding that outlier from the analysis because it has an undue influence. Now, if the outlier isn't causing statistical significance and is just blending in, right, and it doesn't have an undue effect, you can consider leaving it in the analysis because, like we said, it's not the outlier that's the problem, it's the undue influence of that outlier. Okay, so linearity, right, is our next test assumption we will look at. So if you're doing linear regression, it's right in the name, the two variables examined, like continuous variables, should have a linear relationship, which could be either positive or negative. So this may look familiar to you. So this is linearity. The first is a positive linear relationship. So you can see as the scores increase on the x-axis, 1, 2, 3, 4, 5, right? They meet on the y-axis, 1, 2, 3, 4, 5. So 3 meets 3, 4 meets 4, 5 meets 5. Then the next is the negative relation, right? So the highest scores here, say if this was income, the highest scores of income, and this was happiness, have low happiness. right? So it's a negative relationship. Then the higher scores of happiness have the lowest scores of income. So positive and negative linear relationships, and you can see it even makes a line, are fine. The trouble is if it's a curvilinear, so it starts going one way, then goes another, that's not appropriate for linear regression. Okay, so the next step, and all this is in the written portion too. So we're going rapidly, but for a slower presentation, just look at the written materials. So homoscedasticity, the homogeneity, meaning the same, of variance. So we're looking at if data points are spread out evenly between variables. So the parametric tests, a lot of equivalence of variances. So specifically what it's looking at is if there's equal variance in the independent variable at different levels of the dependent variable, such as income relative to difference scores. So to check, so we can check them at the same time, there's a function in the regression, right? So when we go to SPSS and we do our regression, and we'll check this when we do our actual regression model, you see underlined here, when you click plots in the fourth line, you click plots and then zpred and zresid, and that will give you a scatter plot, and that will rate the linearity and the homoscedasticity. Specifically, you'll get a scatter plot. And if there's a random dispersion of the residual, so each dot's a residual, and this is what you want, there's no pattern. They're just kind of randomly spread out, and they're not crossing each other, right? So that reflects good homoscedasticity and linearity. And lastly, we want to look at multicollinearity. So that occurs when we have a regression model and the predictors are correlated at a high level, right? And that distorts findings. You can't see it. So specifically, what can't you see? Well, it could be the fact that education level is significantly related to pre-post score change, and income level is significantly related to pre-test, post-test score change. But there might be a correlation between the predictors, education level and income, right, that cancel each other out, and neither looks like they're related to the dependent variable. So to make sure that's not happening, we assess multicollinearity. And again, when we do our regression, again here in the fourth line, you'll see there's a function for collinearity statistics, and you click that in the regression model, and this will be in the output. Specifically, you'll get a tolerance value and VIF. Now they're the inverse of each other. So they're related. So you're not going to get one good one and one bad one. Either they're both good or they're both worrisome. But if the tolerance, right, is not below, say, 0.20, and hopefully it'll be higher than that, and the VIF, the inflation factor, should be around 1, right? So when it starts getting up to 2 and 3, that's worrisome. But preferably they're all around 1. That means there's not multicollinearity between predictors. All right, so that's our test assumptions. All right, so next we want to look at the measurement tools. All right, so a lot of checks of measurement tools are done before the study, but one check of measurement tools done after data collection, and is probably the most widely reported, is the checks of internal consistency. Right, so what we're looking at is one construct measured by the several items on the scale. So if they are, right, so if we use 5 items to measure happiness, they should be patterned, right? There should be pattern responses. Right? Now you'll see the Cronbach's alpha is the way to measure the strength of this pattern that reveals if one construct is really being measured. So it should be at least 0.70. and 0.80 and 0.90 is better. So what do we mean by a patterned response? Well, let's say this is the scale measuring happiness, and all these items are combined for the happiness score at pretest, and then all 5 are given again at post-test, right? And then you get the happiness score at post-test. Well, there's a pattern. So if somebody says, how happy are you on that first item? Right, in the last 7 days, I felt how happy. So they say happy, strongly agree. Chances are, so strongly agree gets a 5 for happy. Chances are sad is going to get a 1. Right? So, and the other positive items below that, good, strong, and glad, they're going to be clustered probably towards the happy response, and the sad's on the other side, and vice versa. If someone gave a 5 for sad, all the other items would probably be around 1 and 2s, right? Because it wouldn't seem like we're measuring happiness if somebody gave a 5 for happy and a 5 for sad. So this is how to check internal consistency in SPSS. So let's look at that really fast. So it's actually pretty simple. So you analyze, and then scale, reliability analysis. And this could be stretched out, which is good because you don't want a headache. There you go. All right, and then there's all the items. You highlight them. Now remember, feel sad's reversed, so we want the reversed version. Then under statistics, scale if item deleted, continue and OK. There you go. And there's the Chromebox alpha. So that's what has to be 0.70 or above. And we see here it's 0.877. We have our 5 scales. And this is pretty good. All right. So there we are. That's checked. So we've gone through our checks of data integrity. So the next thing we want to look at is actual statistical analysis. So we want to look at univariate analysis, step 4. So what are we asking here? We're just asking what are the characteristics of each individual study variable, right? Just describe each of them, individually. Education level, income level, study group, pre-post change scores. So the univariate test key to the left, you see if the variable is categorical or continuous. Right? You'll see to the right, the univariate test to use is the frequencies procedure. Now, if it's categorical, we want to look at the number and percentages within categories, as it's like education level. If it's continuous, like income, we want to look at the mean score, the standard deviation, and the minimum maximum scores, highest and lowest. So here again is how to produce the descriptives in SPSS. And so if we do that really fast, so we go to Analyze, Descriptive Statistics, and it's all there, and it's all in the written frequencies. Right? And then we would put, income level, our different scores pre to post. Right? And then under Statistics, we would click Standard Deviation, Mean, and here's the skewness and kurtosis we mentioned before. Right? You could even check minimum, maximum if you don't want to look at the actual. Right? And then we could just paste it, right? And then we go to the syntax and run it. And the syntax you just save like any other file. So you see the output tells us the average change score, the average difference score, also called change scores, is 0.18. So the average participant had a slight increase from pre to post regarding happiness. Right? Then we have the highest, lowest, then we report the scale range, It makes the mean more meaningful because you can see the interval from where it falls, the average income in thousands, $39,680, and so on. Then for education level, we can see there's a slight underrepresentation in high school, where there's 24 participants, which is 24% of the sample. In college and graduate school, each have 38%, and our study group is 50-50, split down the middle. All right, so there's that. Then we want to look at bivariate analysis. And what are we asking in that step? We want to know which predictor variables, right, education, income level, study group, are significantly associated with pre to post test change scores, right? So you could look at it in this way. Like, different interventions work differently for different people. There's some people with certain traits that are going to benefit more than others. So one of the things we're looking at is if education and income is associated with higher pre to post test change scores, maybe there's something about income where a higher income somehow enhanced the intervention effect of pre to post test change scores, or a higher education level somehow influenced and enhanced, or it could also lessen, right, the pre to post test change scores. We want to know because we want to control for all the other factors associated with significant pre to post test change aside from study group. Because when we control for those other factors, right, and remove them from the analysis, then we can really pinpoint the effect of study group. Now, it's important to realize if a factor is significantly related to these pre to post test changes, we include it in multivariate analysis, which is the next step, step 6. This is almost like an elimination round, right? So they're either eliminated and not included in step 6, or they're significant and they are included in step 6. So we have the bivariate test key, which will tell you which bivariate test you need, to test this one-on-one relationship between the dependent variable and a predictor. Right? So for example, variable B here is all the same. It's our happiness change scores, right? The difference scores. And then on the left, you'll see the different predictors. So categorical with 2 categories in study group being compared to the continuous dependent variable, we use independent samples t-test. If the predictor is categorical with more than 2 categories, like education level, and we're relating it to the change scores in ANOVA, one-way ANOVA, and if the predictor is continuous like income level, and we're relating it to the continuous change score, we use the correlation. So here is the path to do the independent samples t-test in SPSS. So if we do that really fast, go to Analyze, right, Compare Means, Independent Samples t-test. We click that. Then we can stretch that out a little bit. And then we put the study group in the grouping variable. Now they're coded as 0 and 1. So 1, which is experimental, we put that there. And then 0, it doesn't matter which goes where. Continue. And then we put the continuous variable, our difference scores, here. Paste. And then run it. Right, and there we have our t-test results. I can go back to the slide because it's presented there. And there's our t-test results. Right, so we can see under study group experimental, the mean is 0.3560. So what that's telling us is the average participant in the experimental group had a pretest to post-test change in happiness scores of 0.3560, so about a third of a point. Now, if you look at the control, their average score is 0.0012. So remember, 0.0 is no change whatsoever. So the average person in the control group had, in essence, a score of 0. So their happiness didn't increase nor decrease from pre-test to post-test, but that makes sense because they didn't have an intervention. Now, the next thing we want to look at in the bottom row is the column that says sig two-tailed. So we know there's a difference in the means, but is it statistically significant? Right? Well, we could see that it is because this significance is 0.000. Now, it doesn't make any difference here, but it could. But in the Levine's test, here to the left, if you look at the significance here, it's 0.00. If that's below 0.05, that means the equivalence of means is not equivalent, right? Significantly not equivalent. So in that case, you would use the bottom row. If this was above 0.05, 0.06, and so on, you would use the top row, but they're both 000, so it's a little anticlimactic of an example here, but that's what you would use. So in essence, we know that study group is a significant predictor of the pretest to post-test change. And we can see specifically how much change there was, right? So about a third of a point for the experimental and just about 0 for the control. Now, next, recall, we need to do the one-way ANOVA. Now, recall, the one-way ANOVA is used when we're looking at if the pretest post-test score differences, right, are different for a categorical variable with more than 2 categories, such as education level. If we're going to do the ANOVA really fast, we go to Analyze, Compare Means, one-way ANOVA. Then we put our education level in the factor. And we put our continuous pre to post differences over here. Then under options, we click descriptive, continue, and post hoc, Bonferroni, continue, right? And then we paste and run it. Now, if we run it, these are the results we get. So this is the first part of the results. The descriptives, where we see the mean difference, right? Now in the bottom row, we see the sig is below 0.05. So that means there's a significant difference in the means. So then if we look at the means on the top, we see the high school pre to post test change. The average change is 0.01. For college, the average change is 0.1779. And for graduate school, the average pre-test to post-test change is 0.2842, right? So it looks like that higher education enhances this pre-test to post-test change in happiness scores, right? So the intervention seems to be enhanced with higher levels of education of the study participant. And then if we want to look at which means are significantly different than the others, we have our Bonferroni, comparison. And essentially what this is indicating, now the boxes are reflexive. So the first one actually in this case says it all. That high school is significantly lower relative to college and graduate school, right? That's what the significance indicates and the asterisks. And lastly, we want to look at our Pearson correlations, right? So this is how we're looking at if a continuous variable, such as income, is significantly related to pretest to post-test change. So our higher or lower levels of income, does that enhance the intervention effect of the happiness intervention? So if we go to SPSS, the correlation is actually very simple. We go to correlate by variate, and we just put income level and our difference scores, and we paste them, right? And then we go, right, and click the green button and run them. And this is what we get. Right? So this is the correlation matrix, right? And that's what we want to look at, right? So it's also reflexive. The score at the top is the same at the bottom. So what that's saying is this. We can see or recall the positive correlation is indicated when there's not a minus. If there was a minus in front of the correlation coefficient, which is the 0.56, it would be a negative relationship, meaning as income goes up, that happiness pre to post test change scores would be going down, but there's no minus. So what we see is as happiness scores increase, happiness change scores increase, income also goes up. So it seems like higher income also has an enhancing effect on the pre-test to post-test change scores for the happiness intervention. So if we wrap bivariate analysis up, this is what we see. That all three predictors, the two covariates and independent variable, are all significantly related to the pre-test to post-test change scores and happiness scores. Right? So all three predictors go on to the next step, which is multivariate analysis. Right? Step 6, multivariate analysis.